So it's actually like this. 1 half of f plus g whole square plus minus f square plus minus g square, and this is the sum of measurable functions, which is again a measurable function. So therefore fg is measurable, is a measurable function, is a measurable function. Okay. Now let's do part third of this theorem. Third part, we need to show that mod of f plus and f minus are measurable. So these three functions, f mod of f plus f minus are measurable functions. They are all measurable functions. Let us first do mod of f is measurable. Mod of f is measurable. So we have mod of f inverse. Try to find this one. Minus infinity to a, inverse image of that unbounded interval under mod of f. It's equal to those points of x such that this mod of f of x is less or equal to a. So we are trying to show that this set is measurable. So if we show this set is measurable, it means that mod of f is a measurable function. Mod of f is a measurable function. It's equal to, you can see this is equal to, since mod is always a non-negative number, therefore if a is a negative number, then this set will be the empty set. So it's equal to the phi set if a is negative. And if a is positive, then it lies between minus and plus a, and it's equal to x belongs to x such that minus a less or equal to f of x less or equal to a if a is greater or equal to 0, and that's equal to phi if a is negative number and it's equal to x. So you can write it as its inverse image of this closed interval. It's like this, f inverse of minus a to plus a. It's inverse image of the closed interval, closed set minus a to plus a. Now since f is measurable, therefore this is measurable, and this empty set, it is also a measurable subset of x. So that means in both the cases, whether a is negative and it says positive, greater or equal to 0, whether a is negative or it's a non-negative real number, this set is always a measurable subset of x. So therefore mod of f is measurable. Therefore mod of f is measurable. And therefore mod of f is a measurable function. Is a measurable function. So next we see that f plus is measurable. So by definition, it's this f plus is equal to. Now this f plus is equal to, what's f plus actually? It's equal to maximum of f at 0, and that f minus is equal to, it's equal to minus times the minimum of f comma 0. Minimum of f comma 0. So definition of f plus is it's actually maximum of f comma 0, and f minus, it's minus times minimum of f comma 0. Okay, then you can easily verify this. This f is equal to, the function f is equal to f plus minus f minus, and mod of f is equal to, it's equal to f plus f minus. So from this you conclude that whether the function f plus and f minus are measurable or not. So let's first verify this. F is equal to f plus minus f minus, and mod of f is equal to f plus f minus. So suppose fx is greater or equal to 0. Suppose we first assume that fx is positive, then we assume that fx is negative, and we try to show that f of x is equal to f plus x, f minus x. So case 1. If f of x is greater or equal to 0, that is the first case, case A. So from this we conclude that the maximum of f comma 0 is equal to f at this point, okay, and minus times minimum of f comma 0. What's the minimum of f comma 0? Because since f is greater or equal to 0, so minimum is 0, it's minus 0, that's equal to 0. Okay, so that means f plus is f and f minus is 0. So therefore what's f? Where f is equal to, therefore in that case this f of x is equal to f plus minus f minus, because f plus is f actually. So in that case it's true. And also mod of f, since f is greater or equal to 0, it's equal to f, and that's equal to f plus f minus. So both the equations hold. F is equal to f plus minus f minus, and mod of f is equal to f plus f minus. Now second case, if f of x is less or equal to 0, then maximum of f comma 0 is equal to 0, and minimum minus times minimum of f comma 0. Since this f is less or equal to 0, so minimum is f, it will be minus times f, minus f. So this implies maximum of f comma 0 means f plus, it's equal to the 0 function, and minimum of f comma 0 minus times it's f minus, that's equal to minus times f. Okay, now let's try to find this f plus minus f minus. What's this? It's equal to f plus is 0 minus, it's equal to f. Okay. That's what you need to verify actually. F plus minus f minus is equal to f. And there's some f plus f minus, that's equal to minus f, and it's equal to mod of f actually, because since f is negative, therefore mod of f is equal to minus times f, as f is a non-negative real number, this x. So mod of f is equal to minus times f. So thus f is equal to f plus minus f, and mod of f is equal to f plus f minus. So thus f is equal to f plus minus f minus, and mod of f is equal to f plus f minus. So let's add these two functions. By adding these two, we get f plus mod of f divided by 2, it's equal to f plus, and by subtracting these two, so it means mod of f minus f divided by 2, that's equal to f minus. So f plus is equal to f plus mod of f divided by 2, f minus is equal to mod of f minus f divided by 2. just by adding these two and then subtracting this function from this. Okay, and now you can see that since f is measurable, mod of f is also measurable. So f plus mod of f is measurable, and scalar times a measurable function is a measurable function, therefore f plus is measurable. Again, f is measurable, therefore mod of f is measurable, and this f is also measurable, so the difference of two measurable functions is again a measurable function, and the scalar multiple 1 by 2 times mod of f minus f is also a measurable function, so which means f minus is a measurable function. Therefore f plus and f minus are measurable functions, Okay. Now let's do the last part. The maximum of f and g and minimum of f and g are measurable functions. Maximum of f and g and minimum of f and g are measurable functions. So first we verified that maximum of f and g is actually it's equal to one half of f plus g plus mod of f minus g, f plus g plus mod of f minus g, and the minimum of f and g is equal to one half of minimum of f and g is equal to one half of f plus g minus times mod of f minus g. So let us first verify this. The join of f and g, or you can say the maximum of f and g, is equal to this function. It's one half of f plus g plus mod of f minus g, and the minimum, or you can say meet of f and g, is equal to one half of f plus g minus times mod of f minus g. Okay. So limit star. Let's first verify star. So again, to verify star, as in previous part, we first assume that fx less or equal to gx, then we assume that fx greater or equal to. We take two cases. We take two cases here: fx less or equal to gx and fx greater or equal to gx. So first case, if f of x is less or equal to g of x, then then the maximum of f and g at this point it's equal to g of x. So this one it's g of x. Now we try to find this one. This should also be equal to g of x, and one half of f plus g plus mod of f minus g at this point. Since f is less or equal to g, therefore f minus g is a negative, non-negative. It's a negative number, non-positive number. So that means mod of f minus g is equal to minus times mod of f minus g, because f is less or equal to g here. In this case, it's equal to one half of f plus g, and minus times this minus f plus g. So you can see this is equal to twice g divided by 2, that's equal to g of x. So both the join of f and g at this point is equal to g of x, and this one half of f plus g plus mod of f minus g at this point is also equal to g of x. So thus in this case, if f is less or equal to gx, this one holds. Now we try to verify this second equation. And so that's now let's find meet at this point. Fx less or equal to gx, it's equal to f of x. Okay, that's simple. And let's try to find this one. One half of f plus g minus times mod of f minus g. It's equal to f plus g as it is. Now what's f minus g? Since f is less or equal to g, so f minus g is a negative, it will be minus times. So minus minus plus here. It's plus f minus g. And that's equal to g, and g will go, it's equal to f. So meet is equal to f, and this expression, it's also equal to f. So thus this meet is equal to that one, this expression, and join is equal to this one. So therefore if fx less or equal to gx, these two equations hold. Similarly, if fx greater or equal to gx, you can easily verify that these two equations hold. So thus we have the following. Both the equations holds. Thus, so second case you can do yourself. Case B, when fx is greater or equal to gx. In similar way, you can do this in similar way. So we have the following equations. So thus the join is equal to 1/2 of f plus g plus mod of f minus g, and the meet function is equal to 1/2 of f plus g minus mod of f minus g. Okay. Now it's given that f and g are measurable functions, so therefore their sum is measurable function, their sum difference is also measurable function. So whenever difference is measurable function, the mod of the difference is also measurable, because we know that whenever f is measurable, then the mod of f is also measurable. So both the functions are measurable. F plus g is measurable. This mod is measurable. Again, sum of two measurable functions is again a measurable function. Now look at here. This is the sum of measurable function. It's measurable. And this is the mod of measurable function, because difference is measurable. So it's mod of measurable function, that's measurable. So this is now difference of two measurable functions. It's again a measurable function. So both the functions are measurable, and the scalar multiple 1/1/2 times this is again measurable. 1/2 times this is again measurable. So therefore FAG and FG are measurable functions, as fg mod of f minus g are all measurable, functions, are all measurable functions. Okay. So in next theorem we try to show that the limit of a measurable function is again a measurable function. That we'll do in the next theorem, and we can see in next lecture we'll do that. Thank you.